All right, so I learned something pretty cool that I wanted to share with you, and this is it. And it sort of shocked me a little bit when I saw it. But anyway, let's jump into it. So it was to do with defining a line in 2D space. So hopefully you can recall that the definition of some line in two-dimensional space is ax plus by equaling k. And A and B are obviously coefficients of X and Y, and K can be whatever we like. So over here, we've got values we can change for A, B, and K. Let's just drill down into that a little bit more. So if we look here, if we were to rearrange that, I think you'd be more familiar with it. If we put it in Y equals MX plus C form. So you get Y equals negative A on BX plus K on B. So that's sort of in Y equals MX plus C form there. In any case, if A is 1, and B is 1 at the moment, and K is 1, then we get 1x plus 1y equals 1. And so we get this black line here. Now let's just really drill down into what's going on here. Basically, this line is all the points that satisfy that equation, right? So if we look at this point here, that's on the line negative 2, 3. Well, the x value is negative 2, so negative 2 plus 3 does equal 1. So that checks out. And we can change that, right? Let's pick another point. What about this point here? X value of 0, y value of 1. Well, if x is 0, y is 1, then this equation is satisfied. So that's why the coordinate 0, 1 is on that line. The risk of sounding, I think hopefully you get the idea, but let's do one more. If x is 2 and y is negative 1, 2 minus 1 is 1. So you get all these points on that line. But what's really interesting now is if we change A, right? We can change A to be whatever we like. So maybe we'll make it 2 and we'll make B 2. And we can change K as well. So this is how we define a line in space, right? And then obviously all these points now satisfy this equation, right? Okay, so that's how we define a line in space. Now, the next interesting thing we want to do is I'm going to put in this point here. And I want you to keep an eye on this as I change A, B, and K. I want you to see what happens because this kind of, as I said, was very interesting to me and I didn't know it. So as I change A, B, and K, what do you notice about that point A, comma B? And it's a pretty tricky question, but let's just put it back to somewhere like that. But maybe you'll notice that this point, if I was to draw a vector from the origin to that point AB, just like this, that point is actually always perpendicular to this line. Now just recall this point AB is 2, 3. These are the coefficients of x and y in our equation, 2 and 3. And it's pretty interesting to me that that is perpendicular to it, perpendicular to the line. And when I say perpendicular to the line, I mean it's perpendicular to a direction vector that's pointing in the same direction as this line. So we can put that in. This blue vector D and the black line have the same direction because they're parallel. And so what we can say is that these are at 90 degrees to one another. Now, I really encourage you to think about why they're at 90 degrees. Oh, sorry. Yeah, I encourage you to think about why they're at 90 degrees to one another. If this point AB, if we were to think of the gradient of this line, well, I think you would agree to be rise over run, so it'd be B over A. And let's have a look at the gradient of the black line. Well, the gradient of the black line is negative A over B. So negative A over B and B over A are negative reciprocals of one another. So that's why this vector n is perpendicular to this direction vector d. So I found that pretty interesting. Yeah, so we can say that that is at 90 degrees. There is a 90 degree there, and we can change this however we like, right? There you go. Pretty nifty, huh? Change B to be whatever you want, and you get all this sort of cool stuff. They're always perpendicular. Now, what we could say, if you know a little bit about the dot product, is therefore that when two vectors are perpendicular to one another, we say the dot product between vector n and vector d is therefore equal to 0. And again, if you haven't seen the videos on the dot product, basically means they're not pointing in the same direction at all. They're pointing in perpendicular directions. Remember, the dot product is a measure of how much two vectors are pointing in the same direction. So I think that's pretty cool because this is all true in three-dimensional space. And what I was trying to do, I was trying to wrap my head around a few vector problems in 3D. And then I was sort of able to draw this analogy into 2D. And so when we do go to 3D, it sort of makes sense. Okay. All we're doing now is just adding an extra coordinate. So if we talk about defining a plane in 3D space, we could define it like this: AX plus BY plus CZ equals K. And then it gives you, yeah, this plane here, as you can see. Now, again, for the same reasons as before, in three-dimensional space, this point N, just like point AB, just like our point AB for vector n, our point n here is going to be the coefficients of x, y, and z, which is a, b, and c. So this point n has coordinates a, b, c, and so we get a vector n from the origin to that point. And the grand reveal, hopefully you're realizing this plane that is defined is always perpendicular, and I'm not showing it very well. Maybe I can get it moving a little bit more. Maybe I'll get K involved. There we go. So you can sort of see, if I let that rotate, you can sort of see that the plane and that vector n are always perpendicular to one another. So isn't that nifty? And maybe it's not showing it very well, but hopefully you get the idea. So maybe if I tilt it, there we go. You can see that that's exactly perpendicular there. And then, yeah, it's always perpendicular. So that's pretty cool. And yeah, let me know what you think of that. I think that's a pretty interesting fact. Yeah, good luck with your studies. Let me know if you've got any questions, and I'll talk to you soon.